So in the last class, what we did is that a couple of problems, or in fact a problem on the application of these correlations that we learned. And those correlations were typically for the uniform surface temperature and uniform heat flux. These two conditions we came across that there can be several scenarios where there are several correlations would be available, and we have to apply it depending on the Reynolds number, be it laminar or the turbulent condition. So all the scenarios that we have learned was for the flow over a flat plate. And the problem that we did also dealt with similar case, that here we had a flat plate of known dimension, air was flowing. So we see that which application or which correlations we had to apply and how to get the heat transfer rate of the heat flask. Okay, now today we will see that not only this not only our flat plate, there can be several other objects over which a flow can happen. Okay, so most popular are the flow across the cylinder and sphere. Okay, so in the next, say, after a couple of weeks, when we will see or calculate the heat transfers in heat transfers, heat exchangers, there we will see a couple of terms. One is the shell and tube heat exchanger. There are different types of heat exchanger where actually what happens, this flow, the liquid that is flowing, and also if it is not liquid, some other fluid, it flows both internally, which means if there is a pipe, the flow happens inside the pipe. Also, there are flows that is coming over or across this surface, this whole tube cylinder. So which means we have both the scenarios, that is internal flow, which is happening inside the tube or the cylinder, and we have external flow. So during the calculation of heat exchangers, we need to account for both the types of the flow, and currently we are in the external flow calculation. So typically, say, now these are also called the blunt objects, because say when these obstruct any flow, this kind of shape or the body, the flow scenario is different than the scenario that we have studied, that is a flow over a flat plate. Okay, now here when there is, say, either sphere over which we also calculate, say the flow is coming towards the sphere, and the sphere is basically objecting the flow. So in such scenarios, what would be the Reynolds number? Because we have seen earlier that depending on the Reynolds number, we have different propositions or different relations for the Nusselt number calculation. In that case, for the flat plate, we took the value x from the leading edge, the distance along the flow direction was the characteristic length scale. Or if in fact the length scale was, the maximum length scale could have been the length of this flat plate, which is capital L. Now, in these cases, say the cylinder or say the spherical object, here we calculate the Reynolds number, or say in other words, the characteristic length of this circular cylinder or the sphere are typically assumed as the diameter of the cylinder or the sphere. Okay, so if this is the diameter d, and say the spherical object has the diameter d, so our calculation would be based on Reynolds number, the v, that is the uniform velocity of the fluid that is approaching the object, d by nu. Now, critical Reynolds number for the flow across such circular cylinder or spherical, okay, that in the case of flat plate, we have seen that it is nearly in the order of 10 to the power 5. Here, again, this would be is in the order of 2 into 10 to the power 5. So that means the boundary layer remains laminar for about this much of the value of the Reynolds number, and then it becomes turbulent when it goes beyond the critical value. So when the Reynolds number is greater than this typical critical Reynolds number, then we have the turbulent scenario in these cases. Okay. Now, do you remember the CD versus RE plot for such scenarios? Say this kind of plot. Do you remember if it is RE and CD? The drag coefficient curve for flow over a smooth circular cylinder or say the smooth sphere. Have you seen this kind of graph, or has it been told to you that CD and RE relation for such scenarios when flow is happening across those objects?
No, sir.
No. Okay. Do you know what is stagnation point? No, right? You have not heard this term. Okay, fine. Fine. So, say we have a scenario where we have a sphere, okay, and say my flow is something that is coming So consider this orange thing a spherical, the smooth uh, cylinder. Okay. Now it has a diameter d. Fine. So say the center is here. Fine. The mid plane, say, is this one. Okay, so this is, say, the 90-degree angle at this point. Quite naturally, here we have the 90-degree cross-section. Fine. Now, say a fluid approaching this cylinder. Now, the cylinder is basically placed like a way that it's one side, or say the opening is facing you, and the other opening is deep inside this plane, the computer screen. Okay. So now this is lying in an air. So a fluid is approaching, so the air is approaching to it, towards it, and it is obstructing that flow. Okay. So what happens? The boundary layer actually develops like this, the schematic that I have drawn. Okay, and it will try to wrap around this cylinder surface, that is around this green line. Okay, now what happens as the fluid strike this cylinder surface? This is the midpoint, okay, where its velocity, the fluid's velocity, is lost. It comes to a stop, complete stop. Now, quite naturally, if the flow there completely stops, then it increases the pressure to a very high value. Okay, and pressure decreases as you go along the direction of the flow, as the velocity increases. The pressure decreases as the velocity increases. So at a very low Reynolds number, low in the sense the Reynolds numbers is much lesser than 1, the fluid that comes or approaches towards this spherical object, say the cylindrical object, okay, now it completely wraps around its surfaces. Okay, and it meets the rear end of the fluid at a certain point. Okay, so if the velocity is very, very low, it completely wraps the surface towards the rear end as well, and then the flow again happens, the boundary layer. So basically, the point is the fluid follows the curvature of the object for Reynolds number much lesser than 1. But as you increase the Reynolds number, what will happen? That the fluid will wrap around the frontal area of the object, but then it starts to detach from this area, this points, at these positions. Okay, that is the top surface or the top point of the cylinder, top and bottom surfaces of the cylinder. Now, as the boundary layer detaches from the surface, that means a separation points occur at the rear end. Okay, so what will happen? The flow will not wrap around exactly like it did for Reynolds number much lesser than 1, but this meets at a point in the rear end. If this is the frontal point and this is the rear end, at a point which is far away from the surface of the object. Okay, Fine. So what happens? That means there is a separation region behind this cylinder. Now this region, okay, so this region is called the wake, region, because of wake formation happens. So here there are recirculation, ADs, all the things that are being created or generated. And the point where this velocity comes to a complete stop is called the stagnation point. That is at the mid plane junction on the front area of this cylinder. Any question? Now this happens when Reynolds number increases or starts to increase, and beyond a critical Reynolds number, this flow detachment happens. Now, once this wake formation or the wake region is there, it is typically realized by the vortex formation. Okay, the flow vortices will be there. The pressure would be much lesser than the stagnation point pressure. Okay. Yeah. Any question? Any someone was trying to say something? Steven, you were trying to say something?
No, sir.
Okay. Okay. So this is the scenario that happens when there is a blunt object in a flow field. Now, our objective is to realize or to calculate what is the drag coefficient. Now, we know that the drag coefficient both depends on, say, the friction drag and the pressure drag. This pressure is basically the drag comes from the pressure difference between this stagnation point, that is in the front side, and the opposite low pressure side, this difference. And the drag, this friction is mainly basically is principally occurs due to the skin friction. So drag force that dictates, or say that is also related with the drag coefficient. Okay, so the drag force, if I write as FD, this FD primarily happens due to screen friction drag if the Reynolds number is low. The reason is that when the Reynolds numbers are low, then this separation region is not far enough. At low Reynolds number, boundary layer basically wraps around the whole body of the object. At very critical, say at a very low Reynolds number, this is the region we call the creeping flow. Reynolds number much lesser than 1. There is no separation region. The whole boundary layer takes the curvature of the flow of the object. As you increase the Reynolds number, there is this clear wake region formation where the pressure is much lesser than this stagnation point. And then the pressure drag starts to dominate in the drag force term. So typically, the things can be said that if Reynolds number is say lesser than 1 in such scenarios, in such flow scenarios, then the drag force is primarily due to the friction drag. For Reynolds number greater than 5,000, the drag force is primarily due to the pressure drag. But both these drags, the friction and the pressure drag, are significant when you have intermediate Reynolds number. Now the point is the relation between this drag coefficient for cross flow. I mean, this is the kind of a scenario that we can term as cross flow across a cylinder or a spherical object. Okay, it has a behavior for different Reynolds number, and that is what I plotted earlier. This is a schematic, not to the scale, but the nature would be similar. That say till a low value of Reynolds number. Okay, low means say Reynolds number much lesser than 1. Now typically CD versus RE plots you have seen, if you have seen for other scenarios, this is done in a log scale. Okay, so this is done typically in log scale. So typically what happens that for Reynolds number nearly 1 and lesser than it, or less than equals to 1, we have a creeping flow condition, and there this CD, the drag coefficient, okay, decreases with increasing Reynolds number. Okay, and it is the typical value. It comes like this kind of scenario. For sphere, you know what is that value. What is the relation between CD and RE? For creeping flow? Anyone? Do you remember this relation? Yes or no? Tell me, someone.
Is this for sphere, sir?
Yes, that is what I'm saying. That for Reynolds number much less or near about say 1, less than equals to 1, we have CD is equals to 24 by RE. And there is no flow separation in this region. And this happens for a Reynolds number value that is 1 till this part. So you have a particular slope there. As you increase the Reynolds number, say till about 10, okay, the flow separation starts to occur on the rear side that we have just discussed here. And this vortex shedding starts to occur at about Reynolds number nearly 90 or 100 in this region. And it increases with increasing Reynolds number up to 20 power 3. Okay, until this region, The drag is most, at this, when there is a separation at 10 to the power in the order of 3, there the drag force is principally contributed by the pressure drag. So the drag coefficient continued to decrease with increasing Reynolds number in this range. Now, are you confused with the situation that, or when I'm saying that with increasing Reynolds number, drag coefficient is decreasing? Do you have any question on this? That if the velocity increases, does it mean the drag will also decrease because drag coefficient is decreasing? Anyone?
So this should be the pressure, friction drag that is decreasing, but the pressure drag is increasing.
I am writing as a whole CD, the drag coefficient. So what is the relation between FD and CD? Do you remember?
FT divided by half rho V square into A is equals to CD.
CD. Okay, so that means F is equals to CD multiplied by V square.
Yes, sir.
Agreed? Now this compensates the increase in the drag. So drag force would increase. Although CD is decreasing, but you have a term where the velocity to the square in that order, FD is increasing. Okay, so this actually compensates or offsets this decrease in the drag coefficient, and that is why the FD increases as you increase the Reynolds number. So do not confuse with this. The thing that we are mentioning is the CD or the drag coefficient. Okay, so in this range as well, so there is a decrease in the CD. Okay, then comes your, say, the Reynolds number range, which is 10 to the power 3 to 10 to the power 5. We can call this as the intermediate range or the moderate range of Reynolds number. Here, the drag coefficient remains nearly constant. And this is the behavior by which you can recognize that this is a blunt body behavior. So here, the flow in the boundary layer is still laminar in this region, but there is flow separation region past this object, that is this shaded area that I have mentioned. And in this region, or when it crosses the cylinder, okay, the flow is highly turbulent with vortices or vortex eddies here. Okay, and then there is a sudden drop. On the, when there is a high Reynolds number, then there is a sudden drop, and this drop is in the region of Reynolds number 10 to the power 5 to 10 to the power 6. Or usually beyond this critical number, which is 2 into 10 to the power 5 after this region. this sudden drop, or say this loss of this drag coefficient, reduction of drag coefficient, okay, is mainly due to the fact that the boundary layer now becomes turbulent. Until this point, we have the boundary layer which was laminar till a point, or say at this plane, and then when it passes this or crosses this object, the flow becomes turbulent. But now here, the whole boundary layer is turbulent. Now, what happens with that when the boundary layer is turbulent? The separation point occurs at a far distance away from the body. It moves the separation points to further rear end of the body, and that reduces the wake, or so the magnitude of wake, and that contributes to the lower pressure drag. Okay, so this is the characteristic curve. Now, this is the same similar curve exists, or say the similar line exists when we have say a cylindrical body, smooth cylinder. This is the typical behavior of a sphere. Similar curve exists for the cylindrical body, smooth cylinder. Usually, okay, the separation happens, okay, when the boundary layer is laminar. So you have this kind of a body. This is laminar, the boundary layer. This is our, say, mid plane. This is our stagnation point. So this is our stagnation point. Now, nearly at an angle of theta is equals to 80 degree, the flow separation occurs when the boundary layer is laminar. And this theta is 140 when the boundary layer is turbulent. And that is why the stagnation point, the wave formation region, or say the separation point, goes at the far end or the rear end of the body in case of the laminar boundary layer. Any question?
No, sir.
Okay. Fine. So then there are scenarios where I mean all the cases that we have discussed here, we assumed that the surfaces of these objects are smooth. There is no roughness. Okay, now presence of roughness, okay, the presence of this surface roughness rather, okay, usually increases the drag coefficient, that particularly in the case of turbulent flow. That is why, if you remember, you had seen a diagram. I want you to tell me the name of the diagram where you had encountered several lines for the surface roughness.
Mori diagram.
Mori diagram. And there, those roughnesses were in the turbulent flow region, if you remember, because the surface roughness increases the drag coefficient in turbulent region, and this typically, I mean, this is actually happens with the say streamline bodies. That means when it is aligned with the flow streamline, the object. However, in case of this blunt body scenario, when there is a cross flow, okay, so that Moody's diagram and all these things you have seen when there is internal flow, right, Varun?
Yes, sir.
Which means your surfaces, these inner surfaces, the walls were in line or parallel to the streamline, isn't it?
Yes, sir.
Those are called the streamline bodies or streamline scenarios. But here we have blunt bodies which is obstructing the flow. So in these cases, an increase in surface roughness actually decreases drag coefficient. Okay. So why this happens? Because once it is the surface roughness is introduced, okay, what happens? The onset of turbulence immediately occurs, or onset of turbulence is aggravated. Okay, and once this is done, you can understand that in such cases where the wake formation happen, I mean, it happens at a far rear end of the body, so the magnitude of wake and its contribution to the pressure drop reduces considerably. So you are disturbing the laminar development or the laminar flow by introducing the surface roughness of these blunt bodies, and you are onsetting or triggering the turbulent boundary layer condition quickly. And for that, we have seen that there is a decrease in the drag coefficient. Okay, so it's a typical magnitude. If I try to give an example, say at Reynolds number at 10 to the power 5, okay, for a rough sphere, okay, CD is basically 0.1 with E by D, epsilon by D is basically 0.001. This thing you are aware, what is this value? Surface toughness, the magnitude divided by the diameter of that. Whereas for a smooth sphere, the CD value is 0.5. Which means the drag coefficient you are reducing by a factor of 5 just by introducing some roughness of this magnitude. However, when you cross this region where the CD drops considerably, as we discussed, the same scenario, if you have, say, Reynolds number 10 to the power 6 in this order, okay, so the for same scenario, CD in one case is 0.4 and in other case it is 0.1. This is for the smooth one. This is for the rough one. So it changes its magnitude. It basically reverses the trend. Because once you make it rough, the surface roughness, okay, it increases drag at very high turbulence. The point is that the bottom line, you can think of that roughening a surface can be beneficial in reducing the drag, but that will happen within the appropriate Reynolds number range. If you do not take care of that, that is going to adversely affect your design. For this flow scenario, your drag coefficient decreased if you increase the surface roughness when the Reynolds number range was in the 10 to the power 5. But if you operate the same sphere or same design for a higher Reynolds number, for which you didn't design this one, then what will happen? You would encounter much higher drag, say, which would be a kind of 4 times here, 4 times increase drag. So the bottom line is that you can find from the, say, hydrodynamic or the fluid flow behavior, okay, the drag coefficient. Once the drag coefficient is known to you, okay, your task is typically to calculate the drag force acting on the body for such cross flow phenomena. And for that, you have to multiply that with the area on which it is acting. Okay, so that area for a cylinder, okay, because remember the cylinder is placed like the long surface here and like this kind of a scenario over which the flow is happening. So A on which the drag force is acting is basically the length of this L and the projected diameter, projected characteristic length, which is the diameter of this body. For the sphere, this A would be pi d square by 4, the projection of the area on which the drag force is acting. Because we need to apply this relation FD is equals to CD multiplied by A rho V square by 2. These are the calculation of A. So remember, it is the area which is facing the flow, the projected area that is facing the flow or obstructing the flow. So for that, what we do, similar to our previous calculation, we at first analyze or calculate what is the Reynolds number. Depending on the Reynolds number, we find out what is the value of CD, and then we apply in this relation to find out what is the drag coefficient, the total drag force. Similarly, so once this is done, we are doing this parallelly. If you have observed that we are talking about CD, and at the same time we are now looking at the Nusselt number. Okay, now here, like we have seen in the earlier cases, that there are several scenarios exist, or several relations are available in order to estimate Nusselt number. The point is that this understanding of this flow pattern actually influence your heat transfer understand, or heat transfer that is happening. Because see, this variation of the local Reynolds Nusselt number across or around this surface or around this body, the periphery, okay, you would find there is also the local Nusselt number variation, like we have understood the drag variation. So when we have, say, theta is equals to 0, which is the stagnation point, the Nusselt number value is relatively higher, and it decreases as we increase the value of theta, because we have a thicker laminar boundary layer. Now, depending on the value of Reynolds number, because this influences the velocity on which it is approaching the object. Now, as we have discussed that theta at 80° for laminar boundary layer flow separation happens. Similarly, this Nusselt number, if you write it this way, Nusselt number around the periphery, the local Nusselt number that is varying with theta, it reaches a minimum at this angle. Then again, it increases with increasing theta as the flow then starts to cross the body due to intense mixing in the separated region, because there is wake formation. Wake formation means the eddies or the vortex formation where the flow circulation happens. And if there is recirculation is happening, that means there is intense mixing. And this mixing always helps us in transferring the heat in a more efficient way. So these understandings are fine, but then how do we calculate Nusselt number when there is a flow across such a sphere or across a spherical object? For those, we have correlations available. And those correlations, if you look at the textbook, you'd find that there's a not simple one. For example, let me write it for one. Okay. In fact, I will write it for both of those, that is the cylinder and the spherical. So say if I write the Nusselt number for the cylinder, it takes a form like this, that we have something 0.62. Reynolds number half, Prandtl number to the power 1/3. By Prandtl number to the power 2/3. Now this has 5/8. The whole thing has 4/3. So it's a complex one basically, but it looks like something like this. That depending on the Reynolds number and Prandtl number, you have a relation for Nusselt number, average Nusselt number to be precise, for a cross flow over a cylinder. These are proposed by researcher Churchill and Bernstein. IN. So similarly, there are several relations. The one that has been given for spherical object is the similar one, 2 plus Reynolds number to the power half plus 0.06 Reynolds number to the power 2/3 multiplied by Prandtl number to the power 0.4. These are the viscosities at the free streams and the viscosity at the surface, if there is any variation due to the temperature gradient. This is done, or this has been mentioned for the spherical object, the cross flow over a spherical object, and this is given by Whittaker. It has a validity region. This also has a validity region. This validity region is Reynolds number and Prandtl number greater than 0.2 multiplied up this. And in this case, it is the Reynolds number in the range of 80,000 and Prandtl number in the range of 380. So each equations, because see, these guys have done experiments, they have proposed this empirical relation. So they cannot do all the experiments for a whole range of Reynolds number possible. So whatever the range for which they have studied, they have proposed such correlations. And these correlations are mostly valid, but sometimes it over predicts or under predicts. The error is 30% also. But when you do not have anything more accurate, you can use these relations to find out what is the average Reynolds number for those scenarios. Okay, so I will stop here today. Do you have any question?